we can start. So in general, there are two ways we can use machine learning for materials discovery. The first one is the forward design, you know. So in the forward design, the objective is like to predict a target property, right? And this prediction could be basically in two ways. The first one is regression, and the second one is classification. So in regression, what we mean is we're trying to predict a number, like a variable. We call it a continuous real number, right? Like, for example, you're predicting the height of people in your class. What are the heights? That you're dealing with numbers, right? Some could be 6'6", some could be 5'5", these are variables, you know. For classification, we're predicting in this time around, um, we're predicting like discrete numbers, right? So using the same example, I said for regression, you're predicting real numbers. Like, is this person 6'6"? Is this person 5'5"? Is this person 5'7"? 6'1"? For classification this time around, the prediction could be, is this person tall or is this person short? So just um, two discrete variables that explain the distinguishing nature of the two classes. Are you tall or are you short? That's classification. For materials discovery, for example, here, the way the pipeline works is you have a material, right? You encode this material in a way that a machine can understand it. A computer can understand it. We know very well that computers operate in zeros and ones, right? Binaries, right? So I cannot just take a crystal structure, like, for example, this is a spoon I have here that is made of steel. I cannot just put it inside my computer and say, hey, give me something out of it. I need to find a way to encode this in a way a machine can understand it. And the best way to do that is using numbers, right? Numerics, ones and zeros, something of in that form, and then after you're able to do that, we can now use a machine learning model to do the forward design, which is more like the prediction. Let's predict the property of this material. Let's predict, the ductility of this material, like how much does it bend? How much does it, like what's the hardness? How hard is the material? For functional properties, can this material be used as a solar cell? You know, can this material be used as a catalytical material, maybe for hydrogen reduction reactions and things like that? You know, so that's more of the forward design. You're predicting the properties. The inverse design is pretty different. The inverse design, you're more or less trying to discover new chemistries. So for example, now I envision that I want a certain material that possesses a specific quality that can be used maybe for solar cells, right? So I'm more like going backwards, right? I know the application, I have an idea of the target, but I don't know the material. I don't know the full picture of the material. So we can use a machine learning algorithm to back propagate in such a way that given a target property, we're able to find the material, right? So in a nutshell, that's the difference between the forward design and the inverse design. In the inverse design, you're predicting new material chemistries, and there are basically two major ways you can do that in materials design. You can use dynamic optimizers, like for example, you can use I don't know if you guys have heard of genetic algorithm, Bayesian optimization. There's one they called swarm particle optimization. There are several optimizers that you can use to learn new material chemistries. We can also use generative AI, just like in the way, ChatGPT works, you type in a prompt and then it gives you whatever you're asking for. Similarly, we can design something like that for materials where we can type in the targets and then it recommends the material for us. That's form of a generative machine learning pipeline, right? So in essence, these are the two main aspects of machine learning for materials discovery. There's actually a third one, right? The third one is to understand physical laws, right? So what I mean by that is there are some laws, like for example, we know like the law of gravity. If we throw something, we expect it to land, that is it's an absolute law, right? In materials design, sometimes we cannot use physics or chemistry to understand some of this underlying nature of physical of laws, that governs materials. And that's where machine learning can be sometimes helpful in what we call unsupervised learning. A machine learning algorithm can be able to map the the material to the target. And in the process of mapping it, it can understand some governing laws, that connects the material or defines the material itself, right? So that's the third aspect. But in general, the two main aspects are forward and inverse design. In this tutorial, we'll more or less handle the forward design. The inverse design is not so hard. It's just a continuation of the forward, but I don't think we'll have enough time to treat it today. So maybe if you guys are interested, we can do that next year for how to, use inverse design models, right? But before you can go into the inverse design, you have to understand the forward design, and I feel to an intermediate level. You need to know what's going on in the forward design. And then that gives you the leverage to address the inverse design. So by definition, what really is machine learning? The buzz with AI is all over the place. But what really does it do, in terms of to a common person or to a in layman terms? So machine learning, by definition, is actually a branch of AI that enables computers to learn from and make predictions or decisions based on data without being explicitly programmed. Let's break it one at a time. So machine learning is a branch of AI. There are several branches of AI. There's one they call deep learning, which is a deeper form of machine learning. You have reinforcement learning. There are other interesting aspects, like people who deal mostly with robotics, they use reinforcement learning a lot in that area, right? So what machine learning does is that it um, it learns from a data, and through that learning, it's able to make some predictions or wise decisions, you know, and it's done in such a way that there is no explicit program to it. I give you an example with this plot, a simple cubical plot, right? Cubical because it's x to the power 3, this polynomial. Assuming we have this point, at -2, -1, 1, and 2, you know, and we're trying to understand the trend, you know, that connects this point, for example, right? We can use, maths, we can plot it, and then we can, use some form of equation, and then we get a perfect fit for this data point. Similarly, that's what machine learning does. So you can imagine like this equation is an explicit program, right? It's explicitly programmed. It's absolute. This equation will always work. If we should put an x value here, it would immediately tell us the y value, and that value would always correspond to this trend. Machine learning is different. Machine learning does the same task, but it does it by learning from its mistakes. So I believe like if you want to train these points, for example, a machine learning will start with like a straight line, like this line that I explained in gray, the straight line here. And then by the time it does this again and again and again and again, it's able to now assimilate the points, and it's able to now give us a function, because that's what machine learning in essence is doing, is giving us a function to model the points. And it didn't do that using physical laws. It only did that using statistics, training and learning from his mistakes, going back to his mistakes, updating its learning process, and eventually it will give us an equation that looks something similar to an explicitly programmed equation. right? So that's what machine learning does, in essence. It's just learning from a data, and then learning from the mistakes. People have there's one funny definition someone told me about machine learning, that machine learning is more like statistics on steroids, something of that form. Or you can say statistics with performance enhancers, because it's just essentially doing simple maths. The maths with machine learning are not complicated at all. They're very easy and straightforward maths, but it does it over and over and over again, using some form of differential calculus too. Okay, so is that clear? Are we on the same page, guys?
Yeah.
Okay,
Yeah.
so let's now start with the data extraction and preprocessing process. So if I should just take you just a moment, I should have put that picture. If I should take you to this picture here, right? So this is more like the flow, you know, in general for machine learning. The first thing is the raw data, right? So you have a bunch of sources, you know, we can select the sources we find to be trustworthy. We can discard the sources that we find not to be trustworthy. And then we can compile this into a database. And then from that, after we've gotten a database, we can do some form of cleaning and transformation of the data. And then we can now represent this data using appropriate features, and then we can now follow up the modeling, right? So in the step one, we're going to start with the data. There are several steps we're following gradually. And yeah, and the first step is more like the data extraction and pre-processing. So what I did was I made this notebook to be kind of self-explanatory, right? Um, and I kind of demonstrated how you can freshly download data sets on your own without any supervision. The brief code below illustrates how to freshly download data from the Materials Project repository. In case you've not heard of the Materials Project, it's a very popular materials hub. It stores about 150,000 samples, and it's a very reliable data set. You can explore different material classes here, you know, um, and sometimes it even gives you some form of specific data set for what you're looking for. So for example, if somebody is working with molecules, you have a molecular explorer that you can check some of the compounds there and extract it. Like for the one working with catalysis, you have a catalysis explorer that you can it's actually the data set is actually compiled from this open catalyst data set. And then you have most of the compounds there, and you can filter to know the ones you want. For organic, inorganic compounds, there's one called the MOF, which is MOF. I think it's the molecular organic framework or something like that. I can't remember. MOF data set. Metal organic framework. Yeah. So if you're working with you know, some form of like hybrid organic and inorganic materials, these data sets can really help you, something like that. You can extract it and you can, play with it, you know. So it's a robust data set, and the materials are actually computed using quantum mechanics. So in quantum mechanics, what occurs there is that it's a physical tool that, you're solving there's an equation called the Schrodinger's equation. You know, Whenever we're operating from quantum level, physical laws cease to exist. So laws like gravity, all this Newton's equation of motion, they cease to exist. They cease to exist whenever we're looking at stuffs from a quantum perspective. That is, we're looking at the atoms, the connection, the bonds, and things like that. And then so that's what this data set does. It solves all these compounds using such forms of quantum mechanical equations. And it does it for both experimentally verified materials and even non-experimentally verified materials. And that's what makes the materials project actually very trustworthy because, when it gives us the results for the experimentally verified compounds, we compare it. So we compare when someone takes it to the lab, someone takes this to the lab and then it gets a result. And then we check materials project, we see their results and they're very similar. You know, that's what makes this repository highly reliable. So if you want to download data sets from here, right, you can just look into these codes to see what's going on. I won't advise you to run this. Don't run this code. We're not going to use it, so that you don't complicate your notebook. If you have already executed it, it's still fine. But so you can just search for material. Like for example, I want to search for all materials in the database that has this formula called the ABC3. And I want it to give me this. I want you to give me the material ID, the formula. I want you to give me the bulk modulus. I want you to give me the energy band gap, the volume, the density, as much as it can provide, it's going to give you. And then we can find a way to compile it, and put it into a database. So the data sets we're going to be using today, I actually ran this code, and then that's what you see here when I asked everyone to run this. So I ran the code and I saved it as a CSV file, right? Like an Excel sheet, right? And then if you should print this, if you should run this, you can see how it generates. So it gives me the material ID from the materials database. It tells me the formula of the material, that's the chemical formula. It tells me like the number of sites, like in this case, there are 5 sites, because if we should add it, like here you have one atom from AC, one atom from AL, and then 3 atoms from oxygen, right? So that gives me ACALO3. And then you have the lattice features, like the edge parameters for a unit cell, you have the angles, and you have some other interesting target properties like the energy of the compound, the stability like the formation energy, the density, the band gap, and so on. So for today, we're going to be playing with this material class that is called perovskites for today. We're going to be playing with this material that is called perovskites. So the dataset used for this tutorial was originally downloaded from the materials project and is currently hosted on my GitHub. The dataset contains 4,557 chemical compounds that are characterized by this. So if we should look at this material from a microscopic level, not even microscopic, you have to go down to an atomic scale to look at it. We're talking about picometers, going down into picometers, 10 to the power, I think minus 12, right? To look into it, you're going to be seeing something that looks like this. And then it's governed by this stoichiometry they call the ABX3, right? You have three distinctive atoms that makes the compound. You have one that is you have the A is normally a cation from the periodic table. The B is also a cation, and the X is like an anion. So if you should look at it, it forms something in material science we call an octahedral. So the B is coordinated by X atoms around it, right? So this is a material, right? It's called perovskite. Is a multifunctional material. Is used in many engineering applications, including catalysis, solar cells, and so on. Any questions so far? Are we good?
Yeah, we're good.
Yeah, we're good.
Okay. So now I think we can begin to run the code. So the first thing to do is, we we enter into my GitHub URL, you know, and then we extract the CSV dataset, right? For those who don't know what GitHub is, it's just a simple place for, storing codes. You have software developers, they normally post their codes on GitHub to encourage contributions and, code development from other software engineers, right? And then if we should read this, there's a there's something called import pandas. So pandas is more useful for representing the data, in a very readable and easy way, right? So these, when you see a representation like this, it's pandas, right? It kind of demonstrates how we can arrange things like in a tabular form and in a very interactive kind of form, right? So on running this, it tells me I just ran for, the head. If I want to, I think it's okay, right? If I just do this and I just run the F, you can see it gives me like the full picture of it. It tells me that there are 4,557 rows and 23 columns. Yeah. Oh, actually, that's what this. And then if we should go a little bit, so we can run this second code, the df.ilock. You can run it. The df.ilock. So it kind of, breaks down all the columns for the first sample. The first sample, that means zero. In Python, we start the first sample with zero, not with one. Python recognizes the first index as zero and not one, right? So if we should look at it for the first sample, it is this material, ACAL03. This is the ID on materials project. You know, um, we can actually verify this material or materials project. If I should click on this, the materials ID, and I copy it, maybe I copy it and I go to materials project, for example, and I search for this material in materials project with the ID, it tells me the material. Like you can see it, ACALO3, it tells me it's a cubic material. So the ID is kind of important. If I click on the ID, it gives me more information of that material. If I click on the ID, the ACALO3, you see it can tell me that this is an interesting cubic material. Material Explorer is an interactive framework, so you can just look at the chemistry of the material and all the properties are well stated, you know, and it can equally give me some more interesting properties. Maybe if I want to see the electronic structure of the material, I can find it here to see the band gap and everything, right? So the materials ID is important, right? I would advise you whenever you are extracting data, always include the ID because it can come in handy for you to do more detailed analysis. And then the composition, we have one contributing atom of the element AC, one contributing one contributing atom of the element aluminum, and one contributing element of the atom oxygen. The edge, it tells me the edge, for those who know material science, you know, if I should type lattice properties, yes, A, B, C, alpha, blah, blah, blah. And I check some images, yeah. So this is what I wanted to explain. So in a lattice, you have something that looks like this, right? You have the A edge, you have the B edge, you have the C edge, and then you have the angles that um the interaxial angles, right? That just tell us the the inclination between edges, something like that. So that's what this is, the A, B, C. You also have the alpha, the beta, the gamma. Clearly, you can see it's a cubic material because these are 90, 90, 90, and these are all the same. And in material science, there's something called a space group. So a space group gives more details to the crystal system, right? Yes, the material could be cubic, but cubic materials, they still have different space groups. So I wouldn't like to complicate you with such details, but just know like there's something called a space group. Such information could be handy for some simulations. And then it tells us that this material is not magnetic at all because the magnetization is zero. So it doesn't have any polarization to a magnetic field. It tells us the total energy of the atom is this, that is from DFT. It tells us the formation energy, which is this parameter is very important because it describes the stability kind of the material. And in general, materials with negative formation energy are seen to be stable. right? And those with positive are seen to be unstable. The energy above Hall is similar to the formation energy. Materials with energy above Hall equals to zero are also seen to be highly stable. So you can see it tells us, is it stable? It says, yes, it is. That is true. It tells us the density of the materials in gram per cubic centimeters. So this is the density, how density just tells us in a way like how heavy is the material, if we should hold it in our hand. The band gap illustrates, the electrical properties. Band gap tells us the electrical properties of the material. In other words, how well can this material react when a visible light is interacting with it? And this is a really high band gap. So in essence, this material is an insulator. It cannot conduct like electricity. The band gap is so high. It tells us that the band gap is direct, which is cool, right? So a direct band gap just tells us, which I'll explain later on, and it gives us the volume of the material. And it tells us that unfortunately for this calculation, they were not able to provide us with the mechanical properties. So mechanical properties are the bulk modulus and the shear modulus, right? So, so this is just like the description of the material. There are more properties you can extract from here. There are more properties, but these are the ones I just extracted because these are the ones I want to play with. Okay, so now the next thing is to, do the data analysis and the cleaning. From what I explained, there are about 4,557 different samples, you know. So let's just do some form of data analysis to see how diverse, is the data we're using for this exercise, right? So from this description, I said the data set is robust, comprising about 83 different chemical elements on the periodic table. The data set also contains some empty cells, like incomplete information, which we have to remove, which will be removed, right? So if I want to check now to see the diversity in chemical elements, we can run this cell, just press the run here. So if I should run this cell here, I can see the diversity in chemical elements. I can see that is overall, like for the elements, I think this is silver, right? Ag, we have 155 occurrences. For copper, we have like 156 different occurrences, right? If I should do a plot just to further, look at it from a better picture, you can see the contributing elements from all chemical compounds. So apparently it's well diverse. We have so many this thing, and we have a lot from oxygen, like oxygen dominates, and this is typical with this compound called perovskites. Most perovskites, the anion, so if you remember when I explained the structure here, right? Remember when I explained the structure of a perovskite here? The anion, which is the X, this X side is is mostly dominated by the oxygen atom, you know. Or we can say it's mostly dominated by maybe anionic elements. It could include, elements like bromine, chlorine, iodine, because on the periodic table those are anions. But more or less, oxygen takes a lion's share of it all, right? So now we're kind of pleased with the chemical diversity. This plot helps us, it just gives us an idea, gives us a feel of the contributing elements from all compounds in the data set. And it also tells us like our machine learning algorithm will be forced, our machine learning algorithm will be forced to learn a diverse chemistry. So it's not like it's just limited to like 10 elements or 20 elements. The machine learning algorithm is going to look into 83 different elements and is going to assimilate the material to the properties. If we should now look at the targets, so I told you that, when I started the lesson, that target properties are more or less, what we want to predict, so maybe a target property like could be the formation energy here, right? Which helps us to calibrate the stability of the material. A target property could be the band gap, which helps us to calibrate the electrical behavior of the material. A target property could be the crystal system, which helps us to determine the conformation, of the material. You know, if we should run this code, so this code, you just press play. If you should run it, it now gives us like a histogram of, the targets. So we can see like our formation energy target, it follows something that looks like a Gaussian distribution, right? You guys remember Gaussian distribution from statistics? It looks something similar in that form. It also clearly tells us like there is no number that super dominates per se. Everything is kind of evenly distributed. For the band gap, however, it's different. We can see most of the band gap takes the number zero, which is okay, is normal, because band gaps um, are broadly divided into two. You have the ones we call zero, and then we have, well, in a way, we call them finite and infinite band gap, right? So, but I don't want to go so much into details into it, not to bring more confusion. Maybe in the future I could explain properly. But just know, like for this data set, we have a lot of band gaps with the number zero, which illustrates that most of the materials in this data set are metals. Materials with band gap equal to zero are conductive materials. So they're metals, not semiconductors or not insulators. And then for the crystal system, we can see like we have like some good representation. We have cubic. In general, in material science, there are seven governing crystal systems in material science, which if you took any undergraduate materials course, you should know. You have the cubic system, the orthorhombic, the monoclinic, the trigonal, the triclinic, the tetragonal, and the hexagonal crystal systems, right? So these are the seven primitive crystal systems. They are kind of well represented in these data sets. Right. So now we can move on to check. We now want to check to remove samples with incomplete target data. We want to do cleaning, data cleaning now, which is important. So if I should run this code, to see the formation energy, it looks like it's perfect, right? Like each cell has a formation energy. Each sample in in the data set has a formation energy, but actually it's not so, because we know we're dealing with 4,557 different samples, so you can't really see this here. A way you could know to check to see if there are inconsistencies is maybe if you should download that data set on a Excel sheet, and then you can now filter to check through it. We can equally do that using codes, right? So if I should run this code, it tells me that there are some samples in this data set that do not have formation energy data. And it gives me the indices of these samples, right? So I can see sample 1687, sample 3979, and sample 4333 unfortunately did not come with formation energy targets. If I should check them, I can see them that, yeah, from the data set, there are NaN values. NaN means, no value, like it's just an empty cell. So I want to take off these three from the data set. I want to take it off because it's gonna create troubles when we do the machine learning. Because if we should pass this data set straight into a machine learning pipeline, is going to raise errors that there are some samples that don't have the targets, right? So to clean it, there's a simple code I put, there's something called drop, you know, and if I should do that, if I reset the indices, it kind of cleans it up everything for me. Now, I'm not going to go too much details into, how the codes were done one at a time. That will be left to you, during your homework, to play around with it. I'm going to be honest with you. You can't learn this thing overnight, right? You need to hit your head on the wall, when it comes to things like this. So you have to rehearse, play with it, practice with it. Each line of code that you see, run it separately, for each line to see what it does and print the results. And it now gives you a feel of what everything is doing, right? So now, apparently, I've dropped the wrong ones. I've removed the rules with the incomplete data. And if I should check now, samples with no formation energy data is showing me zero, because I've taken them off, right? So my data set is now clean. Any questions so far? Surprised there are no questions.
You're explaining pretty well so far, so yeah, no questions.
Okay, sounds good. I'll take that as a compliment. Okay, so we can do that. So, I just did for the formation energy, right? I can equally do that for the band gap, right? To check, because I equally want to predict band gap properties. If I should check for the band gap, it tells me that it's clean, samples with no band gap data, they're none. So I don't have problem with the band gap. If I should check the magnetic properties, similarly, so it's equally clean, right? So I've apparently cleaned the data set, and I can now use it for training. So now we move to step 2, which is the future engineering. Hmm. The future engineering and compaction, you know. So like I explained before, we've passed the raw data, we've been able to clean and transform. The next is, how do we represent a material in a form that is readable by a machine? Like I said, we can't put this spoon into the computer. It's not going to understand it. We need to find a way to encode this in a way a machine can understand, right? So there's several techniques. There are a billion, a lot techniques out there, but I'm going to explain to you the basic one, which equally produces good results, like even more sophisticated ones. And that is compacting your features using the average and the standard deviation, compacting. So now let's look at this structure here, the perovskite, the ABX3, right? Because we know, like, this material, the chemical formula of this material is ABX3, right? That's the, um, I'm not sure I can, so the chemical formula is ABX3. That was what I downloaded, right? The ABX3 compound, right? So this has, one A sample. It has another A sample. Sorry, it has one B it has one B element, and then it has three X elements, right? A are cations. I can say cation A. I can say cation B, and then these are anions. Like, these are what predominantly governs this structure, right? Truly, guys, if we should look into this, there are not just 5 atoms. I can count more than 20 atoms here, right? But when we should reduce it to the governing formula, and we're just trying to make things as easy and simple as possible, we're going to have this form. In materials, we call it the unit cell, right? And because I know now that I can represent it using such equations, you know, because I know I can represent it using such equations like this, the ABX3, that tells me a cation A, cation B, and three anions, right? Three anions, I can compact the features into using like an average or standard deviation. For example, I can say if the A atom is maybe calcium, right? If if the A atom, maybe I have maybe like a calcium TiO3, right? Kind of calcium titanate structure. I can use the atomic number of Ca plus the atomic number of titanium plus 3 times the atomic number of oxygen, right? And I divide everything by 5. Does that make sense? You know, does this make sense? Yes, it does, right? So what in future engineering, there's something we call invariance. If I should represent a material like this, right, it kind of describes the uniqueness with that material because I found a way to encode the different atoms that makes up this material into one number, you know. So you can imagine that if I should change this instead of calcium, if I should change this to maybe aluminum, right? So we should be expecting a different value, right? Because machine learning is not like it's not magic. It needs to see the distinguish. It needs to see the differences in the data sets for it to be able to map them to the targets. You know. So what I'm saying in essence is, the average is a very simple and interesting way to do it. I can equally use the standard deviation equation, right, to see how these values vary, right? And that's the future engineering is representing the atoms using their distinctive properties, and then the compaction is let's press everything together using like mean and standard deviation. So each value we get is it represents the material chemistry from an atomic perspective, right? So like I said, I just demonstrated using the atomic number. We can use the group number, we can use the row number, right? All this, like these are periodic table. There's nothing special here, right? We can use the valence of the different atoms. We can use the block, SPDF. The block here represents just the SPDF, you know, SPDF, something like that. So S is one, P, you know the orbitals, right? From basic chemistry. Yeah. So S is one, P is two, D is three, and then F is four. I can use the electronegativity, a very interesting feature. Electronegativity, right? I can use the covalent radius. Covalent radius kind of tells me, the nature of the bonds, could it kind of gives me an information if the bonding is going to be a covalent bond or an electrovalent bond, something like that. I can use the ionization energy. Ionization energy, it kind of gives me the information of um if I should, if I should, just for example, using a laser, right? If I should shoot a laser to this material, how much can an electron jump out of the material? You know, it's just the word, like ionization, when something glows, something like that. How much energy can be expelled, from the atom, something in that form. You have electron affinity. Electron affinity means how much does this atom loves electron, in terms of do I want to take or do I want to give? Right? Something like this, I feel oxygen will be very high because, oxygen does not want to give. Oxygen doesn't want to give because in its orbitals, it needs just two electrons to fill its outermost shell. So oxygen doesn't want to give, you want to take, and that's what the electron affinity can tell us, you have the molar volume itself of the material, and so on and so forth, the ionic radius, the polarizability, specific heat. I mean, you can just type these properties on ChatGPT and it will tell you like what thermal conductivity means. I think everyone here should know what thermal conductivity means, right? It just tells us the ease at which heat flows through a body. That's thermal conductivity. How easy does heat flow through a body? You'll be expecting something like copper to have a high value. You'll be expecting something like oxygen to have a low value. So we can use all this, right, to describe the material, and then we can now create. So I need to run this. Please run this thing, guys. This and all this that you see here, I developed it myself from first principle. So there are actually some libraries that could help you, but I mean, this is actually a library, right? Because this is my own work when I started my doctorate. So I had to develop a library for such properties. So you can run this, and then once we've run this, we can move to the next cells. So the next one we can do is we can create a table. So next is how do we organize the futures, right? We can create a table that correlates the chemical element, to the number of occurrence. So for example, I said like if you see the calcium titanate, right? Calcium in this chemistry has one element, titanium has one element, and oxygen has three elements, right? If I should run this code, I'll explain to you what each line of code does. I'm just using a random sample in, right? We have 4,557. And remember, I took off three, right? So now we have 4,554 samples, right? So I'm just randomly selecting one just for illustration, like number 518, sample 518, right? And then I want it to give me the formula. Can I run this? I want you to give me the formula. I want you to give me the composition and the elements. So if I should run this, this is what it's going to print out to me. It tells me the formula for that sample is calcium carbon oxide, right? CaCO3. It tells me the composition is like this, 113. It breaks it down for me properly to tell me calcium has one, this, and I can organize it like in a table, right? And this is going to help me when I want to do my future compaction because I want the codes to understand that for calcium, take only one occurrence. For carbon, take one occurrence. For oxygen, ensure you take three occurrences and find the average and find the standard deviation, something like that, right? So now let's transform this into a machine readable form. For example, let's use only the atomic numbers. If I should run this code, for the atomic numbers, I'm getting something like this. So, these are the full atoms. You have calcium, you have carbon, and you have the three oxygens, right? For calcium, the atomic number is 20. Yeah, so you can see like the periodic table here. It's two. Anyway, for calcium, you can see it's 20. For carbon, the atomic number is 6. And for oxygen, the atomic numbers are 8. And then I can compact it. What is the average atomic number? So that's 10. The standard deviated atomic number, that is about this, right? So you can see for this material, I've been able to encode it using the average atomic number and the standard deviated atomic number using these lines of codes, right? So when you go back, you can look into it to see what it does. It's just a simple execution. You can run the lines one by one. So what you can do is you can extract this line like this. I can copy it. I can create a new code and then I can run it, just one at a time, just to see what's going on. If I should run this, it tells me like 20. With this, you now have a clear understanding of what each stuff is doing. I can't do that because, I don't think if I should explain each line of code, we're not going to finish this tutorial today. You know, I can try another sample, like I tried 518. If I go back here and I just abruptly say the 4,205 and 205th sample, and I run this line, you see, it tells me it's a manganese, boron, and oxygen. And it breaks it down 113. There could be some really funny samples. Like I think there were some funny ones I saw. You see, this one is beryllium, nitrogen, and fluorine. So it's I wish I could find one that is so funny. Mm, nope. Nope. What I'm looking for is something that looks anyway. Mm, mm. There's one I wanted to explain. It just gives a little feel of this. Um, just a moment, guys. I think you need to see what I want to so that if you should see something like that, you don't get too scared about it. You know what it's doing. Just give me this. So this is the same data in CSV form, nothing special here. Begins with AG3. Yeah, this is what I'm looking for. Sample 16. Sample 16, right? I guess it should be 16. Okay. No, it's not actually 16. Insert, this is 0 plus 1. 16. So that's sample 14. Okay, so let's go back and let's see if we're going to find what I want to explain. Are we together, guys?
Yep.
Yeah.
Yep. Yeah. Yeah.
Yeah.
Let's look at sample 14. This is what I want to show you, right? So you can see, like, before it has always been, it has always been like the other way, right? Where you have 113. Now we're having 311, you know. So don't be deceived by the what you see. You have to be robust about it to create a code that interprets, that clearly interprets the chemistry. That's just what I just wanted to point out here. Because someone can design his code to be 113, something like that. So the way you do the multiplication, everything can be 113. But that would you're gonna misrepresent something that looks like this, because this is like 311, you know. Was that clear? Did the weighting justify itself?
Yeah.
Yeah.
Okay. So that's just what I wanted to explain. If I should run, this 311, I come here and I run this as well. So I have, I've always been saying that in the X site is an anion, but some perovskites violate that law. We can see like in the X site is where you have like the three atoms. We're having a metal, which is a cation, and silver, right? So we have 47, 47, 47, then we have sulfur, and then we have bromine. And then the average atomic number for this is this, and the standard deviated atomic number is this. Cool, right? Yeah. So now you can see I just did it for one sample. I was doing it one at a time for each random sample. Let's now construct a loop for all samples in the data set and their transformative chemical properties, right? You can't do this manually. You need to write a code to do it for 4,000. Imagine if you have 10,000 samples or 20,000, right? When I first started my PhD, Excel was actually my best friend, if I should be honest with you. I did most of my things were manually, using Excel. But as I grew, as I became more comfortable, I was able to script things on Excel with Python. And Python is just so beautiful. It takes away the stress. So gradually you get there. Don't get worried. Read the code line. You can see I'm doing for the Z. Z means atomic number. This is the group number. This is the row number, the mean, the valence, the block. Everything I explained to you here, all these properties, electronic affinity, molar volume, everything, right? So that's what I'm doing here with this, and if I should run this, takes about 20 seconds to run. You can run it too. It's about 20 seconds. It's going to give me for all the samples, it's going to print out, the mean, the group number, the row number, the valence, for everything, So you can see with just some few lines of code I've been able to do. Somebody, if he wants to do this manually, can take him 1 week. And I've done that in just 20 seconds, right? So now I've been able to, this code's properly ran, and all the features have been transformed and they've been compacted. The next thing is like, how can I organize into a table form, right? Organize all features into a table form. If I should run this code, so you can see like for each formula, right? Like this is the first compound. I have the Z mean, the atomic number, the mean atomic number, the group number, the row number, and so on, and so on. You have the valence, the block, the standard deviated for each distance. So this compiles everything together, this code here. If I should run this one, it compiles it. So it tells me the shape of the complete futures is 4,554 by 28. There are 4,554 different samples, and each sample has 28 input futures, right? So the mean gives me 14, and the standard deviation gives me another 14. That makes it 28. If I should give you an example of the first futures, so you can imagine this is the mean of the atomic number, the group number, the row number, I don't know, maybe the block, the electron affinity. So the first 14 will probably be the mean, I guess. And then the next 14 will be the standard deviation, similarly, in the same pattern. Right. So now I've been able to, so you can see now what I've done now is for each compound in the data sets, I have features that describe that compound, right? I have, um, you know, it's just like, for example, someone is like this phone, for example, right? I can say features that define this phone. I can say the color is black. Um, the software is Android, unfortunately. The um the model is Samsung, so these are three features, right? I've said the color, I've said the software, and I've said the manufacturer. So it's the same thing. So for this compound, right, I have these features that when a computer or a machine learning algorithm looks into these features, it should be able to uniquely, you know, to uniquely correlate these features to the chemistry you know. So you can imagine that for different materials, you're going to be having different this thing. If I should, if I should print maybe for another compound, let's just compare. If I should print maybe for, I can say maybe the 1000 sample, obviously it's not going to be this compound, so I can just take this off. It's not going to be ACALO3, you know. Uh, mm, mm, yeah, yeah. So this is the compound. Is you can see it's a very interesting and beautiful. I like it's a beautiful compound, right? The X site is titanium and it has three atoms, and then you have tin. Sn is tin, right? And then you have hydrogen, right? So you can see it's different, right? This is 25.2, this is 23.4. Each compound in the data set is uniquely described by certain numbers. That's it. That's in summary is future engineering, you know. So there are other ways, there are more complicated ways you can read or study, but I would advise you to look into this, um, and see. I think this is like the vanilla first, right? So you try this, see if it works, and then if it doesn't, then you can try more sophisticated ones. Right. So now I can equally include the lattice structural features, right? Like edges and angles. I can enhance the features by including, like, when I started, I explained to you the lattice, which includes edges and angles, right? If I should print the head, so this is the data frame. For each compound we have this, that's the structure, the A, B, C, and the alpha. I think it's nice to include them in a way because it just gives more information. So when the machine learning algorithm is learning, it helps. And besides, one thing you should know is, and I guess I'm going to ask the question, see if someone can answer them. If I should enhance the features and I add it, so now, initially we had this, for the ACALO3, We just had the group number, the atomic numbers and stuff like that. If I should show you the enhanced features now, you can see I've included stuffs like the volume, the angle 90, 90, 90, and then the ABC 3.85, this and this. So I want to throw a question. What really is why do you think it's like super important to include such structural features in this case? Why do you think it's important, like instead of like we should not just stop at this level, but we can include structural features, you know? Any question? Any suggestion?
I have maybe an idea. Is it because there's some isomers that have very similar properties, but then when you put the orientation, you could pinpoint more precisely which molecule it is?
That's a good answer. That's a
Thank
good
you.
answer, If I should take you back to my CSV shit, right? And I show you, I think the last one I show you, AG3. Begins with AG3. What's going on? Oh, I'm at the wrong place. Begins with AG3. Yeah. You can see like in the data set, there are three different, they call them duplicates. In material science, like you said, isomers. The proper term is polymorphs. If you know about polymorphism in crystal structures. So you can see if we should represent this material, right, using the features, if we should use only the chemistry, just these three guys, just this AG, S, and BR, you can see like for these three different materials, we will have identical features. But unfortunately, the properties are not identical. So if I should take you to maybe like for these three, let me highlight these three. If I should take you to the formation energy, you can see they're slightly different. The densities are different. The band gaps are interestingly different, you know. So what way can a machine learning algorithm know, to differentiate? Because if we should just stop at the chemistry alone, the machine learning algorithm is going to be confused because it's seeing the same features for different targets, the same chemistry, but they have different targets. So a way to bring some form of, clarity to the machine learning algorithm, some form of distinction is when we include these features. That's what I did, right? Because you can see they're different. So for the first compound, you can see the A site is 6.9. For this smaller one is 4.9 and so on and so forth. And you can see they're polymorphs, right? What I mean by polymorphs is the crystal structure is the same, the chemistry is the same, but the structure is slightly different. You can see for this, the first one is orthorhombic, but for the second one is monoclinic. For the third one is also orthorhombic, but remember I told you that space group also plays a role. So even though it's orthorhombic, the space group are different, right? For these two, they're different, for these two. So you know I can equally encode the space groups. I can encode it into the features. Maybe if you are PM, you're number one. If you're R3, you're number two. I can do unlimited stuffs. It's just someone like is trying to cook a delicious dish, right? You put in several spices until you arrive at the best for that meal. So that's the point I wanted to clear on that. Did I beat that to death?
I guess so.
So now we move to the next phase, which is machine learning. Uh, we move to the next phase, which is now step 3, machine learning. And after this, I think we should be done, right? So basically, what we're going to do is that we're going to train 4 models today. And we're going to do this 3. We're going to predict the formation energy which is a regression tax. I told you in regression, you're predicting continuous values like the height of people in a class, the height. We're going to predict the energy band gap too, which is also a regression tax. We're going to predict the band gap type to tell us if it's a direct versus an indirect band gap. So this is a binary classification. Binary in the sense that it is either you're direct or you're indirect, right? So it's a simple classification. We can also have something called a multi-classification tax. So in other words, there are not just two classes. Here there are 7 different classes. So you're doing multi-classification, right? So these are the tax we're going to do. We're going to be looking at these models. I selected these models, deliberately. The first one is the support vector machine, you know. The second one is the gradient boosting. Third one is the light gradient boosting. And the fourth one is just a simple neural network for multi-layer perceptron, right? The why I selected this was because the working mechanism of some of these models are kind of different. The way support vector will address your data is different from the way a boosting machine will address your data. It's also different from the way a neural network will address your data, right? So their machine learning is still similar, but the working functionality are different, something like that. The first thing we do is we prepare the target properties. So like I said, we want to predict the formation energy, the band gap, and the band gap type, the crystal system type, So if I should run this code, it tells me the shape of the target properties. There are 4,554. For the formation energy, you can see like these are the values, right? For each sample, corresponding to each sample. So we're going to predict these numbers. That's what we're going to do. We're predicting these numbers. Formation energy, like I said, is an important parameter that defines the stability of the material. What the formation energy tells us is literally the name formation. In other words, if we should take this thing to the lab and we make it, is it going to disintegrate after 5 minutes? You know, and in general, materials with negative values are seen to be stable in general. There are some cases where the material could have a negative value and it will still be unstable. It will still disintegrate. So it's a very important parameter. It gives us an idea of, of the material before we spend so much time in the lab. And in essence, that's what machine learning does, right? It's just helping to cut our losses. We don't want to waste so much time in the laboratory, We want to use machine learning to do the pre-screening, and then after that, we can go to the lab to see if we can make them, for something like that. The next step is the future scaling. You know, if I should show you the futures before, you can see like they're all over the place, They have different numbers, This is 25.2, 12.8, 90. So the numbers are they're so cumbersome, right? They're just complicated all over the place. A wise thing to do is to scale everything so that we can operate from a level playing background, a level playing field. There are 2 ways you can do that to scale. You can use the min max scaler, which kind of defaults to 0 and 1. You can equally use the standard scaler, which in a way it standardizes the data to have a mean of 0 and a standard deviation of 1. The standard scaler is very useful if your data set follows something that looks like a Gaussian distribution. It's very helpful. So now if I should scale it, if I should run this code to scale it, for the original features, like for what I showed you, 25.2, this, so you can see the original features. These are the the atomic numbers and things like that. When I use the min max scaler, you can see it reduces everything between 0 and 1. That's what the min max, all the features, it reduces it between 0 and 1, and it does that for each column, right? So what the min max will do is that it's going to look into like the first column. The first column here is 25.2, 23.6, 27.4, 21.8, 36.8, and 22.4. It looks into all the values in the first column. It checks to see which one is the highest and which one is the lowest. and then it interpolates the other values to ensure they're between those two values. So between, and then it now scales it to be 0 and 1, something like that. So you can imagine this is for row 1, this is for row 2, column 1, column 2, column 3, and so on. The standard features, you can see the difference here is that if you should use the standard scalar, you could be having negative values, because it doesn't just do between 0 and 1. It follows a Gaussian distribution, ensuring that the mean is 0 and the standard deviation is 1. Any question with scaling? Someone might decide to scale between -1 to 1. That's equally fine. You just have to, maybe you want to scale to -1 to 1. You can do that too. You just probably need to tweak something with this code to do that. Are we together, guys?
Yeah.
Yes.
The next thing now is let's split the data set into train and test sets, right? The training sets will be used to train the model, whereas the testing sets will be used to evaluate the model to unseen data. So, that's essentially what machine learning does, right? It uses data to train the model, So, Adiola, please mute your mic, please.
Oh, okay.
So, it's just like training a dog, right? So we can use, we can use some certain characteristics to say use this data to work on your knowledge. That's what the training set is. Like use this certain data I'm providing to you, use it to, to learn the similarity between the outputs and the inputs. That's the X and the Y's. And then after you're done training, we're going to use a data that the model has never seen before, and that is the testing data, right? So the testing data is going to evaluate if it actually learned the similarity between the inputs and the outputs, right? So the first thing I do is I'm going to split this data into 80% for training and then 20% for testing, right? I'm currently working on predicting the formation energy. That's why I have EF signifying the formation energy. And I'm using the futures of the min max. I'm not yet using the enhanced futures. I just want to use the enhanced futures were the one I told you if you should include the lattice properties. I'm just using the chemical properties only, right? If I should run this code, it's going to split the data set into training and testing. So the training is about 3,000. I have 3,000, about 3,600 and about 3,600 samples for training and about 900 for testing. And the next thing I want to do is now the prediction. So I said here, please note the difference in modeling type as it relates to regressive versus classification. Regression means to predict continuous values. Classification means to predict categorical values. Good. And also the models, like I said, like I want to use support vector, right? Most of these models, they give you first of all, guys, you don't have to from scratch develop a machine learning model. I remember Elhaj was trying to do that. I don't think it's necessary. You know, our work as material scientists, especially at this level for you guys to, is to take the model that has been developed by computer scientists and statisticians. We take the model and then we use the model, for our own work. And then we can now fine tune the parameters to suit our problem, something like that. So you don't need to, and that's one of the interesting thing with Python. You can see this simple line of code from sklearn, import this. This line of code could be almost 1,000 lines of code that has just been compressed into one line here, you know. Um, The R here denotes regression, and the C here denotes classification. So different, all this similar models, they have different modes. That's why I said you have to know the difference between regression and classification. The same thing we hear, you see like gradient boosting, you have regression and you have classification, right? For more, if you want to know more about this, you can just Google sklearn. You know, if you should Google sklearn, it gives you it's one of the most interesting database for interesting library for machine learning in Python, right? So you can have different models for classification if you want to do regression, if you want to do clustering, right? You have it all here. If you click on regression, it tells you all the supervised models, right? For everything, linear models, you know, and the documentations are here. Like now I want to use support vector. If I click on support vector machines, I have the documentations here, for classification and, for multi-classification, and so on and so forth. So, depending on your task, the task you have, you can go through it, so on. So if I should run this line of code to import the model, so what I'm doing now is that I'm invoking the models into the code so that I can begin the predictions. This raises a warning. Just ignore it. Now, also, if you want to, even though, like I said, you don't need to develop the codes from scratch, it is important to still have an idea of the working mechanism. Like, why is this doing it this way? What really supports vector? Like, what's going on when the codes are working with gradient boosting? So I encourage that. And if you want to learn more about that, I would advise you to use these YouTube videos. I find it very interesting and very helpful. There's a guy called Joe Starmer. He explains, machine learning models so well, and he does it in a very fun way. Start quest with him. If you check some of his videos, he explains how they work, like what is principal components. He explains the maths in a very comical, and cartoon way to, how support vector works. So you can get to know like the working mechanism. So when I'm using support vector, what really is happening? When I'm using gradient descent, what really is happening? And by understanding that, it now gives you an idea of which model best works for your own application. Make sense?
Yep.
So now let's start with gradient boosting. If you want to know more about gradient boosting, you click on this link, it takes you to the functionality of gradient boosting, right? So this is everything about gradient boosting, the model, you can read about it. So now I'm importing the code, and in the hyperparameters, I left it empty. So what I mean by leaving it empty is if I should take you here, like this is gradient boosting, you can see there's so many things I can use to tune the model. I can tune the model based on the loss. I can tune the model based on the estimators. I can tune the model based on the maximum leaf. There are a billion parameters in machine learning, right? And you can the documentation, it explains what each one does, for each distance. But for now, what I did was I did not put anything. So in other words, I'm using the default. I'm using like the vanilla in this case. If I should train this default gradient boosting model with the training sets, so the X training, that's the features, the input features, and then the predictions, and then I predict, you know, it gives me quick answers immediately. So in 5 seconds, see, in 5 seconds, it gives me the answer. So it tells me that the prediction error, you know, there's a value we called R square. R, R square helps, it gives us an idea of how well does the results fit to a straight line. Yeah, Elhaj, question. Elhaj, you can ask your question.
Yeah, so um like when you split the data, normally you have to like say for example, I'm using like 10 to 20% of the data to like I'm testing 20% of the whole data.
Mm-hmm.
Like, did you do it somewhere?
I don't
Oh,
understand
okay.
your question. Yeah. Did you does this line answer your code? Answer your this thing?
Oh, okay. So it's test size. Okay, perfect. Yeah, it's good. It's good.
Yeah. Some
Okay.
people actually split their data into three. There's one they call training, testing, and then validation, you know. But I don't want to go deep into that. That's more like for um I think that's more like for training deeper neural networks, like deep learning. But for now, let's just stick with training and testing. Yes, Mikhail?
Yeah, just about like the also for the training and testing. So it's like, is it like from the 5,400, the 4,500 like data sets that we have, and it splits 80% of those for training and 20 for testing? Or is it like, is it, or,
Exactly,
okay,
exactly. It's the same data set.
okay,
You know, it's the same data set. It splits it for training and testing, you know. That typically that's a machine learning tradition. It's the
okay,
same data sets. You split it for training and you split it for testing, you know. So that's what I say. You can have one more called maybe a validation set. And it's possible that that validation set has nothing to do with where you extracted the data set from.
yeah,
You get what I
okay,
mean, right?
yeah, yeah,
You
yeah.
know,
That makes sense.
yeah. So that is called transfer learning. It's a more complicated distance, but let's just stick to this
Yeah,
for
thank
now.
you.
Okay, so when I ran the predictions, right, for the formation energy, I was getting the R. I was explaining that the R square explains, you know, how well the lines fall in a, oh, I don't have it. I'll show that later on. How well they fall in a straight line. You will see the implication of the R square value later on. In general, I feel your most important, I feel this is Erickson's theory, right? Your most in a regression task, I feel your most important um error metric is the R square. I feel because the R square gives me an idea on how good my prediction is because you know it's based on percent. It's based on percent. The mean absolute error is is also a very good parameter. But the problem with the mean absolute error is that it's based on the unit of the target. Like now I'm predicting formation energy, right? The unit of formation energy is the unit of formation energy is EV per atom, right? That's the unit of the formation energy parameter, you know. So what this tells me is that for this prediction, my error was about 0.2930 electron volts per atom. To somebody who doesn't really understand, you know, the data distribution, he may be confused, like, what do you mean by that? But if I should tell him that I'm getting an R square of about 83% on the test set, you know, is universal. How much percent did you get? You know, something like that, you know. But believe me also, the MAE is just as important as the R square, you know. In fact, if you're publishing any paper, they want to see your MAE. You know, MAE, I'm not going to explain the statistics or the formula that you can go and read to know what is mean absolute error, what is the mean squared error, and things like that, right? But the good thing also with these values is that it gives me an idea of which model performs better. And also, you know, for error, the lower the better, right? So now I'm having 0.29. If I should use another model and I get something lower than this, then it means is better. Obviously, for the R square, the higher the better, right? For the R square, the goal is to approach, for R square, the goal is to approach 100. For absolute error, the goal is to approach 0. So now when I did this, I said I used vanilla. I didn't put any I didn't tune any hyperparameter. So now let's compare if we use, maybe we just, raise the bar a little bit and ask the model to do more work, you know. So now I'm saying for this machine, please ensure that the number of estimators is about 3,000. I think if I should look at so here is it in the vanilla, that is the default. The number of estimator is just 100. So I'm increasing this by a scale of 30 or 300, right? Or 30. I'm increasing it by a scale of 30, right? If I should run this now, you see it's going to take a little more time to this one because it's doing more work. In general, I expect the results to be better because now I'm stressing the machine learning algorithm. I'm like I'm giving it so much stress. I'm like, you must give me a good result, something like that. Like I'm overworking it to some way, to some degree. It takes like 1 minute to train. Yeah, Mikhail, you can ask a question now. Please, in
Yeah,
case
just
in case I don't see your hand, just you can always interrupt me. That's fine.
okay. Yeah, I was just wondering, like for the estimators, because obviously the more you do, the better the result, but the more computing time it takes. Like
Exactly.
for like a basic research project, I guess, like the one we're doing,
Mhm.
how many would you guys expect for us to use?
It depends, it also depends on the size of the data set. If you have a large data set and you do this, like, see now, I just have about 4,000, right? And it's still running for more than 1 minute. So imagine if my data set was 100,000. I may probably come back tomorrow to get the answers for this result you
Yeah,
know. So it all depends. The thing with machine learning is experiment. You have to play with it. You have to make mistakes. You have to get frustrated sometimes too. You have to keep on tweaking and tweaking. You know, I will
yeah.
explain something about hyperparameter tuning that could help you. Yeah, David, jump in.
I was wondering, is it possible to let the computer or AI select the hyperparameter by themselves, which is the salary our testing?
Yeah, it is. I have
Okay.
one here. I have one here. I'm going to explain hyperparameter optimization briefly.
Okay.
I'm going to explain it. Yeah. Okay, so it took me 2 minutes on the dot, and you can see you can see it improved, right? Initially, it was 0.29. Look at it, 0.19. So the error really dropped. The R square on the test set. We're always looking at the test set. We only look at the trained set just to understand if the model is overfitting. In machine learning, we have something called overfitting and underfitting. You can go back to study more about that, later on. But what you just need to understand by like now you can see it seems like from this indication, I can see my train set is about 99%. This means that the machine learning algorithm actually memorized the training set. It learned it, it understood it so well, the train set, that the R square is 99%. But then when we test it on a data that it has never seen before, right? We trained, we got 99%. We test it on a data it has never seen before, it's giving me 88%, right? So technically it overfits, but it's still fine. It's still fine in some cases. So it depends on what are you developing your model for. Sometimes especially in some cases, I build my machine learning model so that it memorizes the data. I want it to overfit the data so well. I do that mostly for generative learning. It's a more advanced distance. Some of the models I built, you know. But for now, let's just stick with the test set. So now we see that we increased the estimators and we're getting better results. Let's look at support vector now. So we do the same thing with support vector. You just run the code for support vector machine. We're getting a very poor result of about 0.30 here, you know. So it's looking like gradient boosting is a better model. So with support vector, I'm going to explain hyperparameter optimization briefly, right? So like, when I showed you this, you can see there are a billion parameters, right? And it may take so much time to begin to tweak them one at a time. Like instead of squared error, for example, should I change it to absolute error or should I change it to hover? Instead of like what estimator should I use 100? Should I use 1000? There are too many things to tweak here. Too many knobs. You know, one way you can use to bypass all that is something called the grid search CV. So grid search performs an exhaustive search over a specified parameter grid in order to find the best combination of hyperparameters for a given model. So look at this now for support vector. Initially here I didn't put anything, it was completely empty. But here now I have all this. I have, so I'm actually, what I'm telling the model to do is I gave it a bunch of kernels. So look for the one that is best. A bunch of C parameters. Look for the one that is best for gamma, epsilon, and so on, right? If I should run this code here, it's going to take me at least 3 hours to get the results, and I did it yesterday, at least 3 hours. So we're not going to do that. But when I eventually ran it, I got this as the best hyperparameters. These were the best. So using grid search, it's looking into, you can imagine how much permutations it's doing because it's checking linear versus this, poly versus this. Is doing so much permutations here, right? And then eventually it told me that if I should use this value, this value, this value, and this value, it's going to give me the best results. And that's what we're going to use now. So for your homework, I would advise you to, try this, instead of using this line of code, use this one, you know, use this one and then see how you can play with it to tweak it. And this doesn't only apply for support vector, it applies for any algorithm that is hosted by sklearn. Any algorithm hosted by that sklearn, this interesting sklearn. Yeah. So now let's just do this, for this, and let's see the results, for the best, and you see the improvement. Oh boy, I really wanted us to finish within 2 hours, and it seems like I'm going to rush now. Okay, so now we can see the MAE is about 0.24, right? Initially, the results in the first one we got was 0.30. You can see it clearly enhances the prediction. Is it better than this one? Okay, this is still the best. This is 0.19. So gradient boosting it still tells us that I'm the best, in this case. We'll try multi-layer perceptron, so just run the code too. Later, you can look at the works functionality. So with multi-layer perceptron, I put the verbose to be true. What I mean by verbose to be true is that it tells me how it's doing the iteration. So you can see when the code first starts, the error is terrible. The error is very high. And then as it learns and learns and learns and learns, the error is dropping. The error drops, the error drops, and the error drops. And eventually, it gives me that is this. But it tells me a warning. It tells me that I told the code to do this for 100 iterations, but the result hasn't converged, something like that. So what in essence, what it's telling me is that because I put a bottleneck in the code, a bottleneck, I told it just run this code for 100 times, and the warning it raised is that 100 is not enough. I need to give it more because the error is still dropping. The algorithm is senses that the error can still, get better, So if I should increase it maybe to 1000, the iteration, I increase it to 1000. I put this to false because I don't want it to print 1000. I don't want it to print 1000 for me. I just put that to false. And I run it. I think it takes like 2 minutes. And I guess obviously we'll get a better result, right? So the model exhaustively learns. Good. It's still 11 seconds and it's still, well, 0.31. So not bad, eh? Now, this is one of my favorite models. It's called the light gradient boosting. I really like it. I like it because it's a faster model to the general gradient boosting. It kind of it kind of it kind of upgrades from this, So if it should take me 10 minutes to get a result here in the gradient boosting, if it should take me 10 minutes to get a result here, I expect that with this one, the light gradient boosting, it should take me 5 minutes and probably might even give me a better result with the light gradient, So if I should run this now, I increase the estimators to 4000. I think I can just compare the results with gradient boosting. With gradient boosting, I put 3000, right? 3000, and I got this result. So I can come back here to light gradient and I can put 3000 also. Let's just compare the two results together and then let's see. Run. Are we together so far? Are you guys running the codes too?
Yeah.
Okay. When you do, if you should do yours, obviously I think we'll be getting slightly. Okay, let's see. So with gradient boosting, with light gradient boosting, I'm getting 0.1796. I want to check if it's better. You see, it's better, right? This was 0.19, So you can see, and it was faster. I remember when we did this, it took us almost 2 minutes on the dot. But with the light gradient boosting, it does the same thing. It does it better, and it does it um, in 17 seconds, right? So I would advise you to use this model more often in your work. It's really good. There's another one called XG Boost, Extreme Gradient Boosting, but they're very similar. I want to do it for about 4000 because I want it to really learn it. If I'm going to do it for 5000, I want you to memorize the data, the training data, and then give me good test data. Do it for 5000. Let's see the results. I believe it should give me about 0.15. I don't know. Maybe, let's see. Well, it didn't work so well. Still the same thing. It's fine though. It's still the best so far. But the R square, I think it went up to about 89%. Before it was 88%. Good. So now I can do a plot, and I'm going to explain what this R square value is. So run this code, the plots, run this code here. It's going to show me a plot, So now let's see. With light gradient boosting, I'm getting an R square value of, no, that's not it. It's giving me the R square of the training set. I want it to be of the test set. I want it to be of the test sets. Is everyone there? You're going to change something now. Change this to test. The train, change it to test. Anything you see train, just change it to test. Test. Because it's printing the memorized train. I want test. So just change it to test and then run it again. Did you guys see what I did?
Yeah.
Yeah.
So just change the train to test
Yeah.
and then run it again. Yeah, so now it's giving me the proper values, right? So R square is 89.95. So we can compare now, this gives us an idea of how good the model is. And this is what I mean by the R square. The R square, it illustrates how well the points fit to a straight line. So I can imagine like points that are really close to the straight line, you know, it means the actual is the same as the predicted. So the machine learning algorithm, the predicted value is similar to the actual. For support vector, we can see like most of the data points are, it's not as, streamlined as this one, you know, and you can see obviously the R square is lower. So that's why I told you R square is like a really good value. It gives you an idea immediately on the spot on how well the actual values are the same with the predicted values. The predicted values are the one from the machine learning algorithm. The actual values are the one from when we extracted the data set. You know, data points like this one here was not properly predicted. Like something like here, because the actual was about 0. The actual value here was 0. But the machine learning algorithm predicted it to be like -3 for this red dot here. Predicted it to be like -3, right? Yeah. So obviously those errors are bound to occur, right? But in summary, I enjoy that most of them fits on a straight line better. So obviously we can see light gradient boosting is better than support vector, you know. So believe me, you could run a code for your work and support vector will be better than light gradient. That's the amazing thing with machine learning. In machine learning, there's this saying that there is no free lunch anywhere. What that means is don't fully believe that what happens here, what happens for a certain case is generalized to all cases. You have to experiment with different models. And sometimes, and surprisingly, the model you never believed, to do a good work, that model might shock you, might surprise you, in such a way, So experiment. In one of my studies, in one of my Mm. In this study that I think I shared it with you guys, I experimented with 13 different models, you know. So I used gradient boosting, kernel ridge, support vector, you know, decision tree, other boost, experiment. There's no harm. You can see you don't need to script so much. It's just for each model, you just need like 5 lines of codes for each model. So you can experiment, compare the results, and then know what best works for you in your prediction. Finally, let's move to classification. Then we can call it a day or an evening. So like I said, with regression, you're predicting continuous values. With classification, they're distinct stuff. So here now I want to say we're now checking the band gap type. Is it direct versus is it indirect, right? So this is just an illustration for direct versus indirect. In a direct band gap, we say the valence band and the conduction band, they properly align. In an indirect band gap, they're kind of different, the valence band and the conduction band. The good thing with the direct band gap is that an electron can easily jump from the valence band to the conduction band without so much energy. But for this one, if an electron from the valence band wants to jump into the conduction band, it requires more energy. So in solar cells application, they always prefer materials with a direct band gap because we know we're going to consume lesser energy when um, when electrons are moving from valence conduction. So in a nutshell, this what we're doing is it's important for electronics engineering. As simple as what we're doing, it's a big game, for people who work with solar cells, in their modeling. So we're going to do a classification to see direct versus indirect band gap, right? If I should print the data sets, I can see like I have about 3,000 data that have indirect band gap. So false means they are indirect. And I have just about 678 that are direct. So apparently this data set is highly imbalanced, right? If I should train a machine learning model to learn this, certainly the machine learning model is going to be biased. It's going to be biased towards the indirect because there are more data for um, for the indirect, right? It learns more with it. Yeah. So a way to address this is we can do some form of data augmentation, you know. So one of them is the synthetic minority oversampling technique called smooth, right? So what smooth does is that it just creates, for the minority, like in this case now, I have minority to be direct. So what smooth does is that it uses some interesting form of unsupervised learning to augment the data set so that they can have equal sizes. Something about that. If you want to know more about it, you can read this paper. This is one of my papers that I um I published free, on Cornell University, ARXIV. So it just explains how, you know, if I should show you, for example, a prediction here, you know, downsampling versus oversampling. I think I did this prediction for crystal classes. You can see like for downsampled, you can see you have smaller points. But when I use the oversampling from the smooths, you can see like all the points are more like the same. There's data augmentation or something like that. So it kind of helps. Sometimes it helps the prediction, sometimes it doesn't when you augment the data. So you can read that paper, it could help you, right? So now I do the first thing, I split my data set into 80 for training and 20 for testing. I split the data set first. It's important to mention that when you want to do data augmentation, do not augment the testing sets. That's what I stated here. Note that the task with oversampling is conducted only on the training data. This ensures that the original samples that are subjected to testing are not compromised. We don't want to compromise the testing sets. We'll leave the testing sets exactly as how the data platform gave it to us. But for the training sets, we can play with it, we can oversample it. Because if we should oversample the whole data set, we're going to be cheating, you know, in such case, because we're using synthetic data points for training, for testing, which is not a good machine learning practice. Any questions so far as we're concluding?
It's all good.
Okay. So
So
now
good.
if I should run this line of code, you know, it's clearly shows me you can see how imbalanced the data set is, right? I have about 3,000 indirect and just 1,000 direct, right? Yeah, that's what this is, just a plot to explain. Now I want to apply the smooth algorithm. I want to apply it now, the smooth algorithm to take care of the imbalance. And remember, I'm doing it only on the training sets. I'm not doing it on the testing sets, only on the training sets. If I run this line of code, now it's been able to give me equal size for both direct and indirect, equal size. So what Smooth does is that it looks into the smaller data sets. It uses some form of unsupervised learning, and then it synthesizes new data points for us, new data points on its own using unsupervised learning. Yeah. Now, if I should I can now do the prediction, right, with the training. I'm using a classifier here. You can see I'm no longer using the regressor. I'm using the classifying mode now for light gradients. If I run this, it gives me so that it's done. And then if I print the results, You should know that the metrics for classification is different for regression. With regression, because we're testing values, we're using mean absolute error. But for classification is different. Classification, we use something called accuracy score. We also use something known as, I think the accuracy score is easy to understand to anybody. Accuracy just means what is the percentage of corrected predicted classes, So when you did the prediction, how many did you get right? Something like that. And from this, it tells us that the model got 85% of the testing points, the points in the test set, it got 85% correctly. That's not too bad, right? In the prediction. ROC is another metric, and I put the definition for ROC here. ROC just basically indicates, the better performance, with a score, that represents this. So you can just read it later. The ROC just tells us if the machine learning algorithm guessed, like, did you really guess or did you learn? Something like that. I'm getting about 70%. So I think it learned to some degree, if it was 80, it would be better, because anything from 50% means the machine learning algorithm just randomly guessed. But so 70 means we're 20% better than random guessing. I can print the classification report, right? So it gives me a full breakdown of what's going on, in respect to the indirect and direct. It tells me that when the machine learning algorithm learns the indirect, it's getting a score of about 92%. So the machine learning algorithm clearly is able to to distinguish indirect. It knows it. It knows when it's indirect. But the machine learning algorithm, it's struggling for the direct because it's just 50% for the direct. So it struggles with the direct. And obviously, you should know why it's struggling for the direct, right? Because we did the synthetic for the direct, because we did not we didn't we did data augmentation for the direct, something like that. So I feel that's what kind of affected the performance because it's seen a lot of synthetic stuffs and it's not able to understand like what's really going on, something like that. I can for this report, this is the report, the final score is about 86%, which is the same thing with this. The corrected predicted class is 86%. That's the same thing with this. If I should plot the confusion, there's something called the confusion matrix. It gives me something like this. So it tells me the indirect versus the direct for actual and predicted, something like that, So it tells me, you can see it does so well for the indirect, you know. Um, all in total, there was about 719 plus 72. Actually, there was 719 plus 56 indirect samples, right? And out of all of them, the machine learning algorithm was confidently able to predict 719 to be correct and 64 here to be correct for direct. Guys, this is where we call it a day. In the next codes, you can, learn it. You can work on it at home. What I want you to do is to see how you can do like some multi-classification tasks. In this one, we did just binary. So multi-classification, we're now doing like maybe for 7 different crystal systems. But instead of oversampling, there are 2 ways in doing classification when you have an imbalanced data set. In our case here, we could see that we had more indirect and less direct. Is it possible for us, instead of me to create synthetic data sets, another way I could do is that I could reduce the indirect to ensure they have the same value with the direct. So everything should be 678 samples for each class. The only problem with doing this is that I'm going to be losing information because my data, the the data set is going to be reduced, right? Almost by about 40% reduction in data set size. But you can try that, compare the results with downsampling and oversampling. That's what I did here, right? I compared the results between downsampling versus oversampling to see if I was getting any improvement in the performance for crystal system. And besides this paper, it did the demonstration for crystal system. So you can read it to see, how it works. And then you can now see if you can write the codes for the multi-classification. I was trying to do it, but I didn't have enough time. So you can disregard all these codes. And, I wish you happy coding. Any questions so far?
Thank you, Erickson. It was very informative. I don't have a lot of questions for now, but I'll definitely spend the next couple days playing around with it, and I'll be emailing you if I run into any trouble.
Yeah, no problem, anytime. Like I said, maybe in the new year, we could do maybe the inverse design. All what we did today was just forward design. We're predicting targets, right? In the inverse design, we're predicting the material, the chemistry itself. So maybe next year we can look into how to do that. But for now, before we can do that, you have to at least have a working understanding of what's going on here, because this is actually basic machine learning, something that I've explained. You know, if you have any question, feel free to send me an email. I'll always try to create time to help as much as I can. Okay.
Okay, thank you, Erickson. Can you hear me?
Thank you.
Yes, I can hear you.
I wanted to ask a question, a very quick one. That's okay.
Yeah.
Okay. So I am not really working with some of these materials you mentioned, but I just thought to myself that is it possible that this machine learning can actually be applied to like composites? Because you mentioned the materials project, which is like a database for a lot of materials. Is it possible to do you think that I can use this what's it called?
I think so. One of the
Okay.
reasons why I think so is because, like in your own case, you're going to be working with mechanical properties, right?
Yes.
And with mechanical properties, these are very important, like the bulk modulus and the
Yeah.
shear modulus.
Yes.
So you can see like for some data, for some samples, they give such values,
Yeah, I saw
you
that
know.
as well.
So it's possible that you can use the data sets to train mechanical properties.
Okay.
And then, you can now find a way. So you can now use that maybe in your own application one way or the other in your own composites,
Okay.
right? So I
Okay.
think it's possible, like
Okay.
for mechanical properties.
Okay. That'll be great. I'll be in touch with you then
Yeah,
based on this.
yeah.
Thank you so much. Thank you so much for your time and for taking the time to share the knowledge.
And worse. Any more question or are we done? I'm actually very hungry now.
No, it's all good.
I think we're
Yeah.
good.
Yeah, we're good.
Okay.
Thank you.
All
So
right.
I
Thank
think
you.
you can stop recording, right? Stop recording, and we can share it later to guys who want to need it. I think Ernest asked that we should please record it so people who couldn't make it, they can use it later. Okay, so I wish you guys a happy holiday.